So now there is a historical moment. Our drop-in session for vibrations and waves overcomes a number of participants of yesterday's Mods 1 lecture.
Okay, so this is the formula you're given for the charge at V times T. And you're asked to find A alpha omega phi. So starting with alpha and omega, there are, well, to find out an omega, you've got to solve the second order differential equation. So some people have tried U over C is equal to, so it's given as 0. Explain what that means. So if the square wave was going between, this is the voltage applied, if it was going between 0 and Vs, then what happens is this is kicking off oscillations. So the square wave we're applying is kicking off oscillations, and the oscillations happen either side of the voltage of the square wave. So each time the square wave changes, it's kicking off a new set of these oscillations, which are known as free oscillations, effectively by giving the system a new what's the word I'm trying to find?
Equilibrium.
Giving the system a new equilibrium point. So when it's either side of 0, this is the equation we want to solve with the 0 on the right hand side. However, we could also solve it for the case where Vs is being applied, and the only difference is we have a Vs on the right hand side, and we'll see in a minute what that does to the solution. But it's nicer to consider the homogeneous equation with the 0 on the right hand side, which is going to give us the oscillations either side of 0. So you could, if you wanted, solve this equation, or you could solve the general equation. The general equation we used in lectures was that one. So this is your decision. Either solve this equation and then identify constants gamma and omega n in terms of R, L, and C. And once you've got your solution, which hopefully will look like that, you can plug gamma and omega n in terms of R, L, and C back in, and then gamma omega n will give you alpha, omega d will be equal to omega. But you would have found these terms in terms of R, L, and C. Or you could directly solve the equation with R, L, and C in it. And you'll come up with something similar, but it will have some combination of R, L, and C instead of omega d and gamma omega n. It's your decision. It's interesting to solve this one. There's more algebra involved, but it's just a different way of doing what we did in the lecture. Sometimes it's nice to see both, because that brings it home actually what's going on. But it's your choice. How do you solve that equation? Well, you don't plug in the solution we've been given, you plug in a trial solution. And the trial solution we chose was because we knew the first order equation came out as an exponential solution. We proposed AE to the mu t to be the trial solution. Plug that into the equation, and we found there were two values for mu. So I'm going to use the general form. So because of the plus and minus, there were two values for mu, and that meant there were actually two solutions. Some constant e to the mu 1t, and also some constant, it didn't have to be the same constant, e to the mu 2t. But each of these solutions, even though it satisfies the equation, only has a single unknown constant in it, and therefore that can't be the full general solution for a differential equation of second order. However, we know that if we put in the first solution, we get 0 coming out. If we put in the second solution, we get 0 coming out. And because therefore the equation is linear, if we added the two solutions together and put those in, what we get coming out is 0 plus 0. So we get the sum of what we would have got if we had put them in separately, because the equation is linear. So we propose that Q is AE to the mu 1t plus BE to the mu 2t is therefore the full general solution. And at this point you should have mu 1 and mu 2 in terms of RL and C, or you could work it out. And then it's a matter of rearranging, and we did it in one of the lectures. And so if you do that, you will find gamma and omega n and omega d all in terms of RL and C. So that will give you alpha and omega. That doesn't give you A and phi. A and phi, during the rearrangement, actually come from the constants A and B. These were unknown constants which will come from initial conditions. So in order to find A and phi, you have to put in your initial conditions, which are at t is 0, the current equals 0 amps. So if you've got a charge, you can differentiate it to find current. Put t is equal to 0 into that expression that you get for current, and then equate it to 0 as your initial condition for current, and that will enable you to find phi. And then your second initial condition, which is given, is that Q is equal to, well, at t is equal to 0, that's that point there, and we assume that the capacitor, or rather these oscillations have settled at the new equilibrium point. So if the oscillations have settled at the new equilibrium point, there's no current flowing because the gradient will be 0 of Q, and therefore the whole voltage that's being applied at Vs must be across the capacitor. If there's no current flowing, the voltage across the resistor is 0, and if the current isn't changing, the voltage across the inductor is 0. So if the entire applied Vs is across the capacitor, that means initial charge is C times Vs, that's in coulombs. So the first will give you phi, and the second will give you A. Have people actually managed to do that?
Yes.
Okay, ask them.
Is it okay if we take both differential equations, just put them into the same form and compare the coefficients next to each derivative?
Do you mean take this equation and compare it with that one and get?
Yeah, I mean, in our school, because our lab with that instruction just said like express the constants in terms of this. So if like it is necessary to prove all of this in our lab.
Yes, we want to see the. If you're going to solve this equation, we want to see the solution to that equation using the trial solution. And the same for this. If you're solving this directly, you want to see the solution directly, rather than. You want to distinguish yourself from the student who's just written down the answer by showing that you understand it. And obviously we might ask you a question on it, in which case you need to have done it and understood what you've done. So actually an interesting little point comes out, which might have mentioned to some people in the lab. So in the past, some students have thought that because current is 0, t is equal to 0, well of course what that implies is that it's got 0 gradient at t is equal to 0. But some students in the past have thought that having 0 gradient must mean that phi is 0, because cosine would have 0 gradient when phi was 0. However, for this expression, we're actually multiplying the cosine by a decaying exponential. So we're multiplying a decaying exponential, AE to the minus gamma nt, by the cosine, that's the cos, omega dt. I've drawn it without a phase shift. Of course, if you multiply those together, even though the cosine has 0 gradient at t is equal to 0, their product doesn't. So the right-hand side of the origin is going to push the cosine down, and the left-hand side is going to push it up. So their product looks something like that. So the 0 of the exponential times the cosine, assuming phi is 0, is actually just to the left of the origin. So if we want to have a zero gradient, you have to shift the whole curve over slightly by that amount of gradients. So you should find that phi, to get 0 gradient at the origin, is a small and negative number. Because we're adding it to cos bt, we're shifting the cosine slightly over to the right-hand side so that the 0 gradient gets to the origin.
Can I ask you something about the laboratory experiment?
Of course.
In exercise 4, it says where for small r, Vc over V in peak value equals to 1 over r. Yeah, Vc over Vg peak value PEAK equals to 1 over r square root of L over Z. But he says when our result is consistent with the expression. However, in this circuit, RB is supposed to be 0. That means it should be supposed to be infinity. Then how are we supposed to prove it, whether it is consistent or not?
Okay, so first of all, we have to be clear what R actually is.
Yeah.
And that comes back to the circuit diagram. So we've got VC, which is the voltage across the capacitor.
Yeah.
Vn is the voltage across the inductor, the resistor, and the capacitor. That's the 50 ohm output impedance. So when they're building that equation, it's basically a voltage divider. It's saying the voltage across the capacitor is I times its impedance, which is 1 over J C. And then if we divide that by the voltage across the inductor, resistor, and capacitor, that's the current I times their combined impedance. So J omega L plus any resistance in that right-hand side of Vn plus 1 over J omega C. Of course, then the currents cancel, and we've got the equation that's shown in the black block. But this R was total resistance to the right-hand side of Vn. So it will be equal to the resistor box if you've got anything set, plus any resistance in the inductor. So that doesn't mean it's impedance, it means if it's got a parasitic resistance that shouldn't be there, but is. And then any slight resistance in the wires.
Capacitors don't have resistance.
So a capacitor is mostly a metal cable connected to metal plates. It might have a little bit of resistance between the plates. Sorry. It will have a very high resistance between the plates. There might possibly be some leakage of current. So there might be some little bit of resistance that allows current to leak between the plates. But mostly in this circuit, the resistance is coming from the wire that goes to make up the inductor. So the wire that makes up the inductor, as we saw when you were doing the bulb, the hotter it got, the higher the resistance. So this R might actually change depending on how you're driving the circuit. Perhaps if you've got it turned up very high in terms of voltage and the resistor's getting hot, or maybe it's a high frequency and the resistor's getting hot, or maybe it's at resonance and the inductor's getting really hot. Then you might find the resistance of the inductor increases. So different experiments, you've probably found different R for the inductor. So the R in this here is resistance to the right-hand side of the
Why is the R in exercise 1 affected when put into really high frequencies? Why would it change impedance?
Okay, very good question. So, okay, so this is going back to exercise 1, where you're driving a resistor box in series with a 100 ohm resistor, and you're looking at the voltage across each of them. Well, clearly the current is going to be the same passing through each of them, because it's just a single circuit. But on your oscilloscope, what you might find is that at high frequencies, the voltage across the 100 ohm resistor is slightly out of phase with the voltage across the resistor box, even though the resistor box itself is set to 100 ohms. So that implies that something is causing a phase shift in the circuit between when we compare the resistor and the resistor box. What sort of components can cause a phase shift?
An inductor and a capacitor.
Inductor, capacitor. If we've got a current travelling along the wire, even if it's a nice, well-behaved wire, it generates a magnetic field around it. More of this in turn too. So even though we don't want it to be inductive, any wire carrying current, it does have a little bit of inductance. So if we draw it for the resistor, we've got a little bit of inductance called parasitic inductance. So V1 is measured across the resistor plus its parasitic inductance, and the same for the resistor box. It's got a little bit of parasitic inductance. So what we've now got, if we draw the impedance for just one of those, is 100 ohms resistance plus a little bit of inductance. So as low frequencies only get small, so the actual impedance of the resistor plus its little bit of inductance is mostly the resistor, so you see it behaving as a 100 ohms resistor. But if you increase the frequency, obviously the ohmic L part is going to get greater. So a little bit of phase angle starts to creep in between the current and the voltage. Well, if both the resistor box and the 100 ohm resistor, if the amount of parasitic inductance they have is the same, they will both be advanced relative to the current by the same amount, and so their voltages will still be in phase with each other and you won't notice. However, if the parasitic inductance is different between those two, one will be rotated relative to the current by a different amount than the other. And I think some people saw that at high frequencies, where the inductive part does actually become a bit more significant. They might see a phase shift between V2 and V1. So this is known as parasitic inductance.
Do you have parasitic capacitance, or that's not a thing?
Oh yes, no, I'm sure you can. Different parts of your circuit, like these two wires, will have some sort of capacitance between them. Very good point. I haven't actually analysed that in any depth. In year 2, what we'll actually do is we'll look at a circuit and analyse it as the wires are just boundary conditions for electromagnetic waves which are spreading out of the source and into the resistors. So you can either analyse it using currents and voltages, or you can analyse it as electromagnetic waves with boundary conditions. So for example, there would be electromagnetic waves travelling from the signal source and into the resistors. In fact, there'd be a right angle to the resistor. energy, electromagnetic energy flowing between.
So what does happen in the low frequency?
Right, at low frequency,
Maybe it's a different shape.
for the inductor. Okay.
No, for the resistors. Go with the resistance.
The resistance. So low frequency for the resistor. What you actually see is some odd shape like that. And that is the transformer that you had to use here. It's not linear at low frequencies. So below about 150 hertz, if you put a sine wave in one side, you don't get a sine wave out the other side, you get something different.
Why is that why is it that the voltage across either resistor also changes at high frequencies? The amplitude. Besides the phase.
So in terms of phase, it would be due to the parasitic inductance. Do you mean in terms of magnitude as well?
Yeah.
So in terms of magnitude, if you think about the length of this line, the length gives you the magnitude ratio between the current and the voltage. And the current's the same through both of them. So let's say that's omega L1 and that's omega L2. So there are the two impedances of different cases where L1 is actually greater than L2. And the impedances have different lengths. So the magnitude of the voltage relative to the current will be greater in one than the other. And it's the same current, so the voltages will be different.
In exercise 3, at the very end, we asked us to design equivalent for MRS system between 7 and 1 watts.
Yes.
How is that different in the situation where we have to what is the
So firstly, apologies that this lab book was actually written by electrical engineering. We used in fact, up until 2 years ago, waves of vibrations happened in their lab before we had our lab here. So their notation is slightly different. So they use MRS, and we would use I can't remember which way around it is now. MCK. I think S might be the spring constant. So that would be the equivalent of the oscillating circuit without the voltage applied. But of course, if in our actual circuit we've got voltage square wave, so somehow in the exact equivalent to that circuit, you have to apply some sort of square wave to this side to change its equilibrium point. So here we had it between, let's say, Vs and 0. So we need to work out what's the equivalent of a square wave in the mechanical case. So this is a voltage. What's the mechanical equivalent of voltage?
Force.
Force. So somehow we have to apply a square wave of force between Fs and 0 to the mass, because the mass is what's doing the accelerating or not. So you've got to try and imagine and think up some mechanical way for a certain period of time. You've got a constant force Fs applied in that direction to the mass, no matter where it actually, its position is. So somehow that has to have a constant force Fs, no matter where it is. And then for the second half, that's got to be 0. So that's actually quite a tricky problem. There's various theories floating around. I've seen some interesting ones. But that would be then the full equivalent.
Which is ratio? This one?
What was the question? Of
The aspect design circuit, like spring extended and mass release of length.
okay, sorry, that's the
That would be
previous
the contrary.
that's the previous question. So here's the mechanical case. Let's say equilibrium point is here, x is equal to 0, and we've pulled the mass to an equilibrium, to a position x naught. So the string is stretched, spring is stretched, and we're going to release the mass from x naught with 0 velocity. That's what it says, and it says what's the mechanical, what's the electrical equivalent of doing that. Well, what we've done is we've stored energy in the spring by stretching it, so it's got initial energy in the spring. So which of the components here is the equivalent, electrical equivalent of the spring? So somehow you've got to initially put some energy into the capacitor with no current flowing, because that would be the equivalent. If you had current flowing, that would be equivalent to the mass actually moving at t is equal to 0. So somehow you have to think of a way of putting charge initially into the capacitor, but making sure there's no current flowing at t is equal to 0. And then at t is equal to 0, somehow this circuit gets connected as shown, and that's the same as releasing then the mass. And again, you have to use your skill and judgment and imaginations to answer that one.
Does reactance affect the real path of the current flowing through the component?
It does, by changing its phase and potentially changing its magnitude as well. Let's say we've got some arbitrary impedance, R plus xj. So R is its resistance, and x is its reactance. So the method of phasors says if the current is in real life I naught cos omega t, what this impedance is going to do is it's going to well, a voltage will appear across this impedance, the impedance itself, as long as this is sinusoidal, will cause potentially a phase shift, and the voltage will be scaled relative to the magnet, relative to the current, accordingly by that impedance as well. So the way we find out how much it's phase shifted and how its amplitude is scaled is in phasor space. So first thing we do is create a complex phasor representing the current.
Cause omega t plus j.
Well, exactly, and e to the j omega t is that. So the real part of this is I naught cos omega t. So we'll draw an argand diagram. Let's say the current it's a complex number I, complex length I naught. So we now multiply it by this impedance Z to get the voltage V. To multiply complex numbers, it's much more convenient to use exponential form. So we need to write this in exponential form. So it's R real parts and X irrational parts. So it's got a length M and an angle phi, and where M is the square root of X squared plus R squared, and phi is our tan X over R. So we can write this impedance Z. So now if we multiply that by the current to get the voltage, if I naught M e to the j omega t plus phi.
And it's the end that changes the magnitude of the real part.
Exactly. So if you change the reactance, you're changing the length of the and of course the voltage now comes out. It's magnitude n I naught. Phi out of the current. And as time increases, these two rotate with the same relationship to. Yeah, that's really good. Phasors, everyone's going, yeah, good phasors. Is anyone actually still totally influenced by phasors? Okay. So maybe next week we can have another go with them and drop in. Okay, it's good to know. Because we'll actually be using them in waves as well.
Maybe just for all of us, could we have one more time, like very quick, like get through what will we be actually doing in our system, like how it will be going on?
Yeah. So check your emails. So what we'll do is shortly I'm going to produce a list of when you need to turn up and repair. I think I know which group everyone's in. If I've got anyone wrong, please email me back. And then we'll give you a new time during your actual hours. Actually, no, scratch that. So what I send you will be the time you're meant to turn up. Otherwise, it'll get confusing. So I'll send out a list of when you need to turn up. Say, if I've got your group wrong, because I know a couple of people didn't change group, please come to the time given and the group given, and then you'll be able to go to a different study group, so that it will all work out okay in the end. So just for next week, go to the group we're given, which will be, for most people, their correct group, but for a couple of people it may be incorrect.
Just about exercise theory, where does this chart
So damping factor gamma is defined by comparison of the equations of our root c over 2 root l. So let's say gamma is equal to 1. And if we rearrange, we get R is equal to 2 root L over root C.
Yeah, but the seconds, like, I don't quite understand what it means and
Okay, so if R is greater than 2 root L over root C, gamma is greater than 1. So that means we're in the realm of heavy damping. If we go back to the general solution, Q is A1 E to mu1T is A2 E to mu2T. Mu1 and mu2 minus gamma omega n plus or minus omega n square root gamma square minus 1. So if gamma is greater than 1, this is now a real, the square root of a real number. Looking at mu1, and mu2, those are both got negative signs in front of them, so this must be a negative real number. Looking at the one above it, well, we've got something that's minus and something that's plus. However, gamma squared minus 1 square rooted will always be slightly less than gamma. So we've got a minus gamma plus, or minus gamma omega n plus omega n times something that's less than gamma. So this will also be negative and real. So the heavy damping solution are two exponential functions added together, where mu1 and mu2 are both negative. One will be larger than the other. So we have the sum of a faster exponential decay plus a slower exponential decay. The solution is just two exponential decays, where these are the values of mu1 and mu2, and that's heavy damping. So it looks like it's the sum of two exponentials, but it looks like an exponential decay towards the equilibrium. So that would be like on your car. If you sat on your car bonnet and then got off it, you'll see the car turn back towards equilibrium because it's heavily damped. If your car was lightly damped, you would feel that every bump in the road. You're doing that all the time.
Can you plug in initial condition to find A1 and A2 too?
Exactly.
But when t is equal to 0, I is 0, right? So at the very beginning, the slope should be 0. Is it true?
Exactly. So you can combine two exponentials to get a zero slope.
At the very beginning.
Yes. So for example, let's say that's the actual cube that we see, but we want to make that up from two exponentials. We can make it from let's say it's got value q0 to the start. So to get a value of q0 for a gradient to 0, one exponential has to have a positive coefficient and the other a negative, so that their gradients cancel out at t is equal to 0. So let's say that's our fast exponential, and let's say no, that's our slow exponential. And then So the initial values are A1 and A2. So we know A1 plus A2 must be equal to Q naught. So the initial values give you initial value Q. And the gradients, those t's equal to 0, must be equal and opposite to give an initial gradient of 0. So if we had those two added together, it looks something like that.
In exercise 4, there's a question about whether our observations of omega peak versus R are consistent. So, like, we weren't really sure how we able to show like what the question was asking.
Okay, that was equal to, is it R? So this question is slightly odd, because it almost works backwards from the next question. So it asks you to calculate it. So you need to find the value of the peak. It's in L and C, so you do need to find the value of C, but you can find that from your capacitor R. And that will give you R. So once you've found R, if it's similar to the R that you've got in previous exercises, it actually turns out, I think, in this exercise to be almost a factor of 10 law sometimes. It's 30 ohms or something. But if it's not too far off, then you verify that at least your R is within the sort of range that could be expected. And it could be that because in this exercise we've got resonance, then there's lots of energy being interchanged between the inductor and the capacitor, so the inductor will be getting quite hot. So it's R might be high. We're just about done, are we? Okay, so just to recap what will happen, check your email. You will be getting a schedule which will tell you when you should come to lab. You need to come in your pairs. There'll be 3 people, me, Pascal and Niraj, and we'll have 3 stations set out with the equipment. Each person will get different questions, and we'll direct those questions to you or your lab partner specifically. So we won't throw a question out and just wait for someone to answer. We want to ask you specific questions.